In this video, I will explain to you a new chapter titled Entropy. But before that, I would like to share with you the learning outcome of this chapter. That is, after completing this topic, you should be able to analyze the entropy changes during thermodynamics processes and calculate the isentropic efficiency of various steady flow devices. What is entropy? Entropy is viewed as a measure of the molecular disorder or molecular randomness. As a system becomes more disordered, the molecules' positions become less predictable and the entropy increases. Thus, a substance entropy is lowest than the solid and highest in the gas phase. In the solid phase, the molecules of a substance continually oscillate about their equilibrium positions. Still, they cannot move relative to each other. Their position at any instant can be predicted with reasonable certainty. In the gas phase, however, the molecules move about at random, colliding with each other and change direction, making it extremely difficult to predict the microscopic state of a system accurately at any instant. Associated with this molecular chaos is a high value of entropy. The total entropy is denoted as the capital S with a unit of kilojoule per Kelvin. And the small letter s represents the specific entropy with a unit kilojoule per kilogram Kelvin. The difference between energy and entropy balances for a system is illustrated in the given figure. The second law of thermodynamics states that entropy can be created, but it cannot be destroyed. The entropy balance is defined as the entropy change of a system during a process equals the net entropy transferred through the system boundary and the entropy generated within the system, and it is shown as the given expression. The determination of entropy change of a system during a process involves estimating the system's entropy at the beginning and at the end of the process and taking their difference. That is, entropy change equals entropy at final state subtract entropy at initial state. Note that entropy is a property. and the value of a property does not change unless the state of the system changes. Therefore, the system's entropy change is zero if the state of the system does not change during the process. For example, the entropy change of steady flow devices such as nozzles, compressors, turbines, pumps, and heat exchangers is zero during steady operation. Entropy can be transferred to or from a system by two mechanisms: heat transfer and mass flow. Entropy transfer is recognized at the system boundary as it crosses the boundary, and it represents the entropy gained or lost by a system during a process. The only form of entropy interaction associated with a fixed mass or closed system is heat transfer, and thus the entropy transfer for an adiabatic closed system is zero. Heat transfer to a system increases the entropy of that system, and thus the level of molecular disorder or randomness, and heat transfer from a system decreases it. The ratio of the heat transfer at a location to the absolute temperature at that location is called the entropy flow or entropy transfer. It is expressed as in the given form. The quantity Q over T represents the entropy transfer accompanied by heat transfer. The direction of entropy transfer is the same as the direction of heat transfer, since thermodynamic temperature T is always positive. The mass contains entropy and energy. The contents of entropy and energy of a system are proportional to the mass. Both entropy and energy are carried into or out of a system by streams of matter. The rates of entropy and energy transport into or out of a system are proportional to the mass flow rate. Closed systems do not involve any mass flow, and thus any entropy transfer by mass. When a mass in the amount of m enters or leaves a system, entropy in the amount of m s, where s is the specific entropy, follows it. Entropy transfer by mass flow is given in the following expression. Entropy balance for any system undergoing any process can be expressed more explicitly as in the given form. In the rate form, it can be expressed as the following. The entropy balance can also be expressed on a unit mass basis as follows, where all the quantities are expressed per unit mass of the system. What we see here is the mechanisms of entropy transfer for a general system. For a reversible process, the entropy generation term Sgen drops out from all of the relations. A process for which Sgen equals 0 is internally reversible, but not necessarily totally reversible. The total entropy generated during a process can be determined by applying the entropy balance to an extended system that includes the system itself and its immediate surroundings, where external irreversibilities might be occurring, as shown in the given figure. When evaluating the entropy transfer between an extended system and the surroundings, the extended system's boundary temperature is taken to be the environment temperature. A closed system involves no mass flow across its boundaries, and its entropy change is the difference between the initial and final entropies of the system. The entropy change of a closed system is due to the entropy transfer, accompanying heat transfer, and the entropy generation within the system boundaries. Taking the positive direction of heat transfer to be to the system, the general entropy balance relation can be expressed for a closed system as shown here. To make it short, the entropy balance relation can be stated as the entropy change of a closed system during a process equals to the sum of the net entropy transferred through the system boundary by heat transfer and the entropy generated within the system boundaries. For an adiabatic process where Q equals 0, the entropy transfer term in the relation drops out. The entropy change of the closed system equals the entropy generation within the system boundaries. Therefore, we could observe that Any closed system and its surroundings can be treated as an adiabatic system. The entropy balance for a closed system and its surroundings can be written as illustrated. The entropy of a controlled volume changes as a result of mass flow and heat transfer. Taking the positive direction of heat transfer to be to the system, the general entropy balance relations can be expressed for controlled volumes as in the given equations. This entropy balance relation can be stated as the rate of entropy change within the controlled volume during a process equals the sum of the rate of entropy transfer through the controlled volume boundary by heat transfer, the net rate of entropy transfer into the controlled volume by mass flow, and the rate of entropy generation within the boundaries of the controlled volume as a result of irreversibilities. Most control volumes encountered in practice, such as turbines, compressors, nozzles, diffusers, heat exchangers, pipes, and ducts, operate steadily. Thus, they experience no change in their entropy. Therefore, the entropy balance relation for a general steady flow process reduces to the following expression. For single-stream steady flow devices, the entropy balance relation simplifies to the following expression. For an adiabatic single-stream device, the entropy balance relation further simplifies in the given form. The entropy change relations for ideal gases under the constant specific heat assumption are presented here, you will use these equations to determine the system's entropy change during a process for ideal gas substances. An isentropic process means the system's entropy change during a process equals zero. That is, the entropy final and initial states are identical or constant. Suppose a system works with ideal gases as the working fluid and experiences an isentropic process. In that case, the relations between the gas temperature, pressure, and volume can be linked through the following equations. These equations are valid for the constant specific heat assumption for an ideal gas. Now, let us comprehend the increase of entropy principle. The entropy change of a closed system during an irreversible process is always greater than the entropy transfer. Some entropy is generated or created during an irreversible process. This generation is due entirely to the behavior of irreversibilities. The entropy generated during a process is called entropy generation. The entropy generation is always a positive quantity, or zero. Its value depends on the process, and thus it is not a property of the system. The entropy of an isolated system during a process always increases or remains constant in a reversible process. In other words, it never decreases. This is known as the increase of entropy principle. Note that in the absence of any heat transfer, the entropy change is due to irreversibilities only, and their effect is always to increase entropy. A system and its surroundings can be viewed as the two subsystems of an isolated system, and the entropy change of this isolated system during a process is the sum of the entropy changes of the system and its surroundings, which is equal to the entropy generation since an isolated system involves no entropy transfer. Since no actual process is indeed reversible, we can conclude that some entropy is generated during a process. Therefore, the universe entropy, which can be considered an isolated system is continuously increasing. The more irreversible a process, the larger the entropy generated during that process. No entropy is generated during reversible processes. The increase of entropy principle does not imply that the entropy of a system cannot decrease. The entropy change of a system can be negative during a process, but entropy generation cannot. The increase of entropy principle can be summarized as illustrated here. This relation serves as a criterion in determining whether a process is reversible, irreversible, or impossible. Steady flow devices deliver the most and consume the least work when the process is reversible. Therefore, work-producing devices such as turbines deliver more work, and work-consuming devices such as pumps and compressors require less work when they operate reversibly. One way of minimizing the compressor work is to approximate an internally reversible process as much as possible by minimizing the irreversibilities such as friction, turbulence, and non-quasi-equilibrium compression. A more practical way of reducing the compressor work is to maintain the gas-specific volume as small as possible during the compression process. This is done by maintaining the temperature of the gas as low as possible during compression, since the specific volume of a gas is proportional to temperature. Therefore, reducing the work input to a compressor requires that the gas be cooled as it is compressed. To comprehend this, we will compare the work input involving three kinds of compression processes, which is an isentropic process involves no cooling, a polytropic process involves some cooling. Finally, an isothermal process involves maximum cooling. Assuming all three processes are executed between the same pressure levels in an internally reversible manner, the gas behaves as an ideal gas with constant specific heats. We see that the compression work is determined by performing the integration in the given equation for each case. With the following results, the three processes are plotted on a PV diagram for the same inlet state and exit pressure. On a PV diagram, the area to the left of the process curve is the integral of V dP. Thus, it is a measure of the steady flow compression work. It is observed that the adiabatic compression requires the maximum work and the isothermal compression requires the minimum. The work input required for the polytropic case is between these two and decreases as the polytropic exponent n is decreased by increasing the heat rejection during the compression process. If sufficient heat is removed, the value of n approaches unity and the process becomes isothermal. It would be desirable to have a parameter that expresses quantitatively how efficiently an actual device approximates an idealized one. This parameter is called the isentropic or adiabatic efficiency, which measures the deviation of actual processes from the corresponding idealized ones. Isentropic efficiencies are defined differently for different devices. For a turbine under steady operation, the working fluid's inlet state and the exhaust pressure are fixed. Therefore, an adiabatic turbine's ideal process is an isentropic process between the inlet state and the exhaust pressure. The desired output of a turbine is the work produced. The isentropic efficiency of a turbine is defined as the ratio of the actual work output of the turbine to the work output that would be achieved if the process between the inlet state and the exit pressure were isentropic. Usually, the changes in kinetic and potential energies associated with a fluid stream flowing through a turbine are small relative to the change in enthalpy and can be neglected. Then the work output of an adiabatic turbine simply becomes the change in enthalpy. H2A and H2S are the enthalpy values at the exit state for actual and isentropic processes, respectively. The isentropic efficiency of a compressor is defined as the ratio of the work input required to raise the pressure of a gas to a specified value in an isentropic manner to the actual work input. When the changes in kinetic and potential energies of the gas being compressed are negligible, the work input to an adiabatic compressor equals the change in enthalpy, where H2A and H2S are the enthalpy values at the exit state for actual and isentropic compression processes, respectively.